So we're going to finish off the chapter here with the law of cosines. Just like the law of sines, as I mentioned in the last video, this is designed for non-right triangles. Do keep in mind that the law of sines and the law of cosines does work for right triangles too. They work for all triangles. We just tend not to use them for right triangles because we have easier methods like SOHCAHTOA, Pythagorean theorem, things like that. So when it's a right triangle, but they do work for those too. We just tend to use these really only for non-right triangles when we don't have other methods. The law of cosines is a little more going on in the formula than the law of sines. It's written in three different versions, though it's not three different formulas. If you just consider a triangle, and what we've talked about in the last video for like the standard labeling of a triangle, here's all you're really looking at. So the A, B, and C represent the three sides of the triangle. This B and C would be the same values as this B and C. The only angle involved is this guy, the one that follows the cosine. The only thing that matters, and what you're seeing in the three different versions of this one formula, is all we're really looking for is that this angle needs to be the angle that is across from this side. So the way I always explain this is, instead of trying to look at this as three different formulas, just think of this as this is the side across from this angle. The B and the C simply represent the other two sides of the triangle. That's it. That's really all there is to this. So that's what we're going to be focusing on for this section. So here's our first page in the notes. I apologize for the pink X complicated story. Anyway, so we're given this triangle. I have this side is 4, this side is 10. We were given the included angle of 32 degrees. So one issue that we're noticing on this is, so why use the law of cosines? Why not use the law of sines? Well, when we look at the information that's been given here, the one thing that we're going to notice that's different about this than what the last lesson where we were using the law of sines is I do not have a complete ratio anywhere in this drawing. In order to use the law of sines, I need to know an angle and the side across from it in order to set up my proportion. Well, if you don't have that information, then the law of sines is not going to work for us here. We need to go to the law of cosines. And so that's what we're seeing in the setup here. So again, I have side C is the side across from the angle that we know. So as I look at this formula, so this is side C, that's the guy that we don't know. This is the angle across from him, our 32 degrees, which means that the A and the B simply represent the other two sides of the triangle, which are 10 and 4. Beyond that, it's not a whole lot more than just plugging numbers into a formula. So that's really all we're doing here is we're just throwing those numbers into the formula. The rest is calculator work. Do be careful. There's a lot going on here. The one thing that you can't forget to do that is often forgotten is this step right here. Right? So we do have to remember that as all of this gets put into a calculator, remember that that still equals C squared, not C. Right? So when we get down to this final stage, I then need to square root both sides in order to get my side length, which came out to be about 6.9. All right, so let me bring you down a little ways. Once you figure out that side C is 6.9, you'll notice that we now have a complete ratio. Right? I now know an angle and the side across from it, so moving forward, I have a choice. I could use the law of sines at this point, if we want to, because now I can say sine 32 over 6.9 equals whatever. I could say sine B over 4, and I could go on to solve it from there. As a general rule, and this is what they're saying in this paragraph right here, as a general rule, it is safer to use the law of cosines when you are finding angles, because you may run into an issue if the angle that you're trying to find is supposed to be obtuse. When you do the law of sines, it's going to always give you the acute version of the drawing. And so if you were to say find angle A, so if angle A or if angle B is supposed to be obtuse or acute, In this drawing, we can see that angle A is supposed to be obtuse. It's supposed to come out as 130.2 degrees, obviously an obtuse angle. If you use the law of sines within that process, it's going to tell you that this is an acute angle, right? It's going to give you the 180 minus this as the result. So it would say it's 49.8 degrees if we use the law of sines to find it, when actuality is supposed to be the obtuse version of that angle. Okay, and so we talked about some of that in the last video. So anyway, the point of that is once you get to this stage, if you need to find angles, much safer to use the law of cosines and not the law of sines. So anyway, what they did from here was they said, okay, let's take the information that we now know, plug it into the law of cosines again in order to find angle A. Okay, and so on this one, here's what you need to now keep in mind about the formula that we're working with, is remember that whatever this side is has to be the one across from this angle. So if I'm now looking for angle A, this is now the isolated side on this side of the formula. So this is going to say 10 squared, and that's going to make these two guys be the other two angles, or sorry, the other two sides of the triangle. The 4 and the 6.9, which are the other two sides of the triangle. Okay, and so that's what you see in the setup right here. Okay, so all that has now been plugged in. Ultimately, because I'm trying to figure out an angle, I am going to use the inverse cosine function at the end of this in order to get my angle. So a little basic algebra first. They said, let's take this piece right here. We're going to subtract it over to the other side. Then we're going to divide this over in order to isolate cosine A. So that's what you're seeing in this big giant setup right here. We're going to take the inverse cosine of all that fun stuff in order to get angle A, which is 130.2 degrees. So we now know him, we know him, we can subtract those from 180 in order to get angle B. And that's what they did in their final step. Okay, so we're going to practice some of that right here. So follow along with me. So again, what we're seeing on this one is angle C is 40 degrees. So that's what we know so far. This is a side angle side case. And so I don't have enough information to use the law of sines. So because I don't know the angle and the side across from it, so I need to go to my law of cosines. So as I go to set up my formula, again, I know that the angle that I'm working with, this is the side across from it, so this needs to be the isolated side within my formula. So I'm going to say c squared is equal to, and now here's my a squared plus b squared, which are just going to be the other two sides of the triangle. Minus 2bc, or sorry, 2ab in this case. And then cosine 40 degrees. So pretty straight shot into the formula. The rest is going to be calculator. Let's type that in real quick. Remember what I said on the last one, how, at the end of it, I'm going to have to square root both sides in order to get c by itself. So usually what I do on these is I actually just start with the square root right off the bat so that I don't forget to do it. So I'm just going to type all this in under the radical. So 15 squared plus 7 squared minus 2, 15, 7 cosine 40. So we're getting about 10.6 for side C. Something I just thought of as you look back at the last one. I mentioned up here that it was safer to use the law of cosines rather than the law of sines. Something I mentioned in our last video was that, I think it was the last video, remember some basic rules of triangles. The smallest side is across from the smallest angle, the largest side is across from the largest angle. If you were to use the law of sines to do this previous problem, you would notice if this came out to be an acute angle, not the obtuse angle, you would notice that your rule has been broken. And so that would tell you, that would like be your hint as to that law of sines process didn't work, because it would have broken the standard rules of triangles. And so that would have then maybe told you, hey, let's take my answer that I just got, subtract it from 180, and that would give you this angle. And now I would know the actual angle for angle A. Just a thought. So one way of sort of getting around this process and maybe using the law of sines instead. Let's move on. Okay, so now, like we said, in theory, I could use the law of sines in order to get another angle. Like we set up above, they do recommend that we use the law of cosines because it's a little bit safer, because we don't know if these are supposed to be acute or obtuse yet. So I did just mention a way we could maybe work around that with the law of sines. So that's kind of up to you. Let's just stick with our law of cosines because that's what they recommend. So we'll go that same route. Let's just start with angle A. So we could do angle A or B, it doesn't matter. I'm just going to pick angle A. What I do want to remember though is that if this is going to be angle A, then this needs to be the side across from it. So my 15 is going to go there, which means the other two sides of 7 and 10.6 are going to be these two values, and those as well. So same formula, but I'm just reordering my terms here. So we're going to look for angle A, which means this is now the 15, which means these need to be the other two sides, which are 7 and 10.6. Minus 2, 7, 10.6. Cosine of angle A. So again, there's our setup. Ultimately, at the end of this, we're going to have to do an inverse cosine to figure out angle A. So let's go ahead and throw that in. Let's rewrite this before we go to the calculator. So in the calculator, just to save myself some algebra here, I'm going to subtract those to the other side. So I'm going to say 15 squared minus 7 squared minus 10.6 squared. And all that is going to get divided by this information, which is the negative 2, 7, 10.6. And that's going to isolate the cosine of A, which means I'll then need to do the inverse cosine of all that. In order to get angle A. So I kind of like doing that first so I can just type all this in one shot. So I'm going to do an inverse cosine. Let me set up my fraction. Start typing here. So, and of course, guys, you could simplify this. You don't have to write 15 squared. You could put 225. You could put 49 right there. So of course you could do those things. I'm just trying to type it all in so that you can see everything as it fits the formula. And I'm also aware that my 10.6 is maybe a little too shallow as far as accuracy goes. We could probably have gone a little deeper on my decimals for that 10.6, but it's too late now. I'm committed. There we go. So there is all of it typed in. So that tells us angle A is 115.4 degrees. So here's what I'm seeing on that then is if I would have used the law of sines, I would not have gotten 115.4. I would have gotten 64.6, right? And so if I then didn't really try to figure out if that was accurate or not, I would miss it and I would think this is my answer instead of this. So that's why they say safer to use the law of cosines to protect you against those types of issues. So anyway, I now know this is 115.4. So we now know angle A. So in order to get my third angle, I can just subtract this guy and this guy from 180. So let's take out the 40. Let's take out our previous answer. And we were left with 24.6 degrees for angle B. And again, guys, you will notice then now with this being 24.6, I now have the accurate scenario of the smallest side being across from the smallest angle and the largest side being across from the largest angle. And that's always a great check. All right, let me keep it moving for you. So here's a scenario where we now know 3 sides and no angles. Not a whole lot different. We're still just going to plug into our basic law of cosines formula. You'll notice I still can't use law of sines because, again, I don't know one complete ratio. I don't know an angle and the side across from it, so I'd have to go to my law of cosines. So they just said, let's just pick angle A to start with, and that's the one they're going to find first. So again, if I'm going to find angle A, this needs to be the isolated side in my formula. These then represent the other 2 sides of the triangle. And the rest is doing exactly what we just did on the last problem. So they took this information and subtracted it over to the other side. They cleaned up this to become 64. And so to finish this one off, they kind of did this in pieces. I think I would have done it really in one big step like I did in the last problem, but that's okay. So if I was going to go their route, I need to divide that 64 over. So they're kind of wanting us to do all this at once. So I'm going to say, let's divide the 64, and then I would have to take the inverse cosine of that information. And that's what's going to go into my calculator in order to come up with angle A. So let's throw that in real quick. So let's do a little inverse cosine, negative 20 over 64. And we get 108.2 degrees. Okay, so we now know angle A. How do we find another angle? So what if we wanted to find angle B next? Let me just fill this in. As we talked about earlier, I could potentially now use the law of sines. And I would probably be just fine doing that at this point because I already found an obtuse angle, which means the remaining 2 angles have to be acute angles. So really at this point, I know I'm safe. I know they're going to be acute angles. I could just use the law of sines. Nothing wrong with that if you want to go that route. I'll just take you through the notes for the way they set it up. But you could at this point use the law of sines. So if we wanted to find angle B, this is now the isolated side across from it. These are the other 2 sides. So if we start plugging in the numbers here, from across from angle B is a 4. So 4 squared. These are the other 2 sides, which we know are 8 and 10. So just plug it into the formula. Of course, as we go ahead and clean all that up, and this is just not a whole lot different than what we've already been doing, so let me jump to this stage right here. Ultimately, I need to take the inverse cosine to finish it off since I'm looking for an angle. I'm getting 22.3. I think they made a typo here. This should say B. This is supposed to be angle B that we are working with, not A. So angle B comes out to be 22.3 degrees. Looks like this. So of course, to find my third angle, I'm just going to subtract the ones that I know from 180. And let's type that in real quick. And that's going to give us angle C. So let me scoot this over. So 49.5 degrees is our third angle. All right. So what we are looking at is the final portion of this chapter. And to finish off this lesson are 2 formulas that can be used to find the area of a non-right triangle. You guys already know that if we're going to find the area of a right triangle, I would just do 1/2 base times height. And that's totally fine if you have a right triangle. But what do we do if we don't have a right triangle? So then we're looking at other formulas. And I'm going to introduce you to two formulas you've probably never seen before. There is something called Heron's area formula. And I'm going to show you that one. That's in our book on page 438. Really kind of a neat formula that you probably haven't seen before. Works for any triangle, that you can get the area of any triangle with this formula. Now, I'll show you the other one on the next page. Let me just pull up this one real quick. So on 438, we're going to see Heron's area formula right here. All right, so here's the formula right here. So it's the square root of all that fun stuff. So A, B, and C represent the three sides of the triangle. So one thing I guess we need to establish first is, in order to use this formula, you need to know three sides of the triangle. So if it's a case where I don't know any of the three sides, then this formula is out. So this is just the case where you know all three sides. So the S that you see is found by this. If I add up the three sides, the perimeter, and divide by 2, I get S. Okay, and so that's the number that's going to go in for all four of those S's right there. But other than that, it's a pretty straight shot into that formula. Let's take a look at one, and then we'll try one on our own. So they said the three sides are 13, 17, 20. So in order to figure out my value for S, what they call the semi-perimeter, they're going to add those three up, divide it by 2, and they get 25. So the rest is plug and chug here. So they're putting a 25 in for all four S's. The 13, 17, and 20 are the three sides of the triangle. And if we simplify it, we have our area. So let's just do one of those for practice. So again, I'm going to find my semi-perimeter, my value for S, by adding up the three sides. Which is going to look like that. See if we can do that in our head real quick. So 36 plus 30 would be 66. Divided by 2 is going to be 33. So there's our value for S. So as we plug this into our area formula, don't forget that square root. So I have my S. And then I find the difference between all these guys. So I got my 33 minus 18. I got another 33 minus 18. And then I got a 33 minus 30. And that's it. The rest is calculator work. I'll go ahead and plug that one in. We've come this far. We might as well finish it off. So I'm going to throw in that square root first. Got my 33. Type in all my values. And we have our area. So about 149.2 would be the area of that triangle. All right, let me introduce you to the other triangle area formula. This is when you have the SAS case. So do understand that the order of this matters. Okay, so when we say SAS, that means I know the angle between the two sides that I also know. Okay, so here's an example. Right, so I know this is called the included angle, right? So if I know these two sides and I know the included angle, so this reads in the order of SAS, side angle side. So if I have that scenario, then I can use this formula. So Heron's area formula was for knowing all three sides. This is your SAS formula. Okay, it's called 1/2 AB sine C. And again, this works for any triangle. But we tend to use it for non-right triangles because for a right triangle, I would just use 1/2 base times height. So this is really just used for non-right triangles, like the one below. So if we were to find that formula, or sorry, find that area, I'm just going to plug into my formula. So 1/2. So the lowercase a and b represent the two sides that I know. My c represents the included angle. So I know the sides of 6 and 10. Sine of the included angle, which is 37 degrees. And the rest is calculator. So Trying to get that glare off the calculator so you guys can see it. Not that you couldn't type this one in on your own, but so anyway, half of 60, so I really could just put 30 right there. So 30 sine 37, and we have our area of about 18.1. All right, so what if, quick what if scenario, and we are done with the chapter. What if I have a case like this? So this is like angle, side. This doesn't fit any of the descriptions that I have. Well, I need to use other information to come up with either these all three sides, so I can use Heron's area, or at least an SAS scenario so that I can use the 1/2 AB sine C formula. So in this one thing we could certainly do is find the missing angle here by subtracting those from 180. So if I do 180 minus 78 minus 40, so 62 degrees is our third angle. We still don't have enough, though, that fits either one of the scenarios we just described, so we're going to need a little side work here. So as I look at this, I can use my law of sines to find a missing side length. So I'm going to say sine 40 over 7 equals, let's go after this guy. So we're going to say sine 78 over something. So this is our x. So a little cross multiply and we can get our value for x. So let's see, I'm going to end up with 7 sine 78 over sine 40. So about 10.65. Is our missing side length. So now you'll notice I now have an SAS scenario, and so now I could find the area by doing the 1/2 AB sine C so that would be my setup, and of course you could just plug that into your calculator and you got your area. Little homework hint down here. Guys, once in a while they do throw in some tricks to see if you're paying attention, I think. So just like I told you before, how like the smallest side has to be across from the smallest angle, things like that, right? So those are all rules of triangles that they assume you're just paying attention to. So keep that in mind. So one thing I added in as a homework hint down here is there can be a case where a triangle does not exist at all, right? And that would be a case where the two smaller sides are less than the third side. So let me give you an example. If I said, and this is something you guys covered in geometry, but let's just say I had sides that were 2 centimeters, 3 centimeters, and 10 centimeters. You could not build a triangle with those dimensions. The sides would not connect, right? It wouldn't be long enough. It'd be having something like this. Let me see if I can draw this. So like, here's my 10. This side is 2. This side is 3. These sides will never come together. No matter how low I bend them, they'll never meet. I can never create a triangle with those sides. So the rule is, in order to even have a triangle, the two smaller ones have to add to more than the third side. So just a helpful homework hint. But other than that, we are done with chapter 5.